to get a running start, I thought we'd start with this slide that we already covered. Okay. So Chapter 5 kind of dives into the science of a few things. Actually, it seems like Chapter 4 kind of dug into the science of gravity a little bit and momentum, okay? And this one we're going to talk about, we talked about energies called electromagnetic radiation, these cousins, right? You see the cousins up there? And some important things, just to kind of remind you how this works, is that each one of these cousins, okay, vary by two things. The symbol for wavelength is, do you remember that little lambda thing? Okay, and then frequency is F. And we said that over here, with regard to gamma rays, you wouldn't want to be hit with gamma rays. They'd be very destructive to our cells. And they have very short wavelengths and high frequencies. Okay? And over here, we said that radio waves have very long wavelengths and they have low frequencies. So the next thing we need to talk about is how those cousins, you're like, why do we have to talk about atoms? Well, I was thinking of a reason to give you, and here's a reason. Okay. Let's see, what was I going to say? Well, one reason, and it's going to take us a little while to get there, but is like early on, like the Big Bang-ish sort of thing, there was only just the simplest atoms. Now, this atom's pretty complicated. The reason I know this atom's complicated is if I look at the nucleus, go back. If I look over there at it's called the nucleus, you might be familiar with it, that's the center of an atom. I call it kind of the chewy center. Okay. I know it's complicated because the earliest elements only had one proton. Okay, and if we go ahead and take, let's take what color is that, pink? Let's take the pink ones to be protons. There are 4 protons there. Okay, that's pretty complicated. And that doesn't just happen. So I'll tell you how that basically happened is over time, stars like the sun take one proton, okay, and combine them, and actually our sun is making something that has 2 protons in it. Okay, so that's one of the things when we talk about stars burning stuff in their cores, we need to kind of talk a little bit about atoms. Okay? But the other thing, and probably more important, and we'll get to it sooner, is that when energies interact with, is there atoms here in this table? Yeah, we're made of atoms, okay. When energy interacts with atoms, okay, it's important to understand the atom a little bit. Okay. So for this course, what I need you to know is the kind of the concept of a nucleus. Okay, you kind of see the nucleus there. Let's see. So this, as I've drawn it, is the nucleus. I kind of call it the crunchy center of an atom. Okay. And then what are these ... here?
Electrons.
They are electrons, but protons was a good guess. In the middle, in the crunchy center, we have protons and neutrons. Neutrons are of a symbol N, and they don't have any charge, so we give them a little 0 superscript. And these out here are electrons. Electrons. Okay, nucleus. Electrons. Nucleus. Okay, you get the idea that electrons are moving? Okay, because they are. So in chemistry, when I kind of talk about an atom, one of the statistics about an atom is that if the nuclei are really small, the nucleus of any atom is very small. I don't care if it's a really heavy atom, it's still very small, the nucleus, okay? And it's crunchy like this. No, it's crunchy like this. But to scale, if the nucleus was this big, something tangible you can hold like a BB, okay? The statistic is the closest electron, okay, the closest electron would be 5 stories high on either side, 5 stories. Okay, so if a story is about 10 feet, yeah, so it'd be about 50 feet away. to scale. That's the closest electron. And the thing about electrons is they're okay to kind of go like several electrons around an atom, but they need their own space. So that's the closest electron. And then beyond that, you get what we call the electron cloud, kind of shown up there. They're getting farther and farther away. Okay, so that's kind of an atom, nucleus, protons and neutrons and electrons. Okay, so I mentioned time of the Big Bang. The simplest element is hydrogen, and I printed them off, but I think they got kind of lost in the printer. I'm going to give you your own little periodic table of elements, just because I can. We aren't talking too much about elements, but the simplest element is hydrogen. Okay, so the symbol for hydrogen is H, capital H. And what we do is to go ahead and, can you see that little superscript 1 up there? Okay, this right here. This little superscript 1 means what we call its mass number. Okay, that is right there, the mass number. And what you do with the mass number is you look in the nucleus. You look in the nucleus. And what's in the nucleus? What two particles are in the nucleus? Not the electrons. Protons and neutrons. You look in the nucleus of an atom, you count them up, and then whatever count they come to, it's going to be a whole number. You put it in that corner up there, and that's what we call the mass number. Okay? The atomic number is the number of protons in the nucleus of an atom. So I get kind of serious with protons. See, I wear my proton shirt. It's the little things like protons today, just for you guys. The thing about protons is it's so important. That defines, I use the word defines. You could use another word, but it just says what element that atom is. It defines the element. Okay? So it defines the element. So hydrogen has only one proton in it. I think in this chapter your textbook has a periodic table of elements. I'll go get one. I'll go get your thing at break. The second one element, most complicated element, would be helium, and it has least complicated. It has 2 protons in it. The next element is lithium, and it has 3 protons in it. I'm going to run out of the ones I know. The next one is boron, and it has 4 protons in it. Okay, next one is, I think, I should know this. Is it nitrogen? It has 5 protons, but I know carbon has 6 protons in it. So you see how we're kind of getting more and more, and you recognize the names of those elements. Okay, and what do they differ? By the number of protons in the nucleus. Okay, so later on, we're going to be talking a little bit about something called isotopes. Okay, it must be on the next slide. Okay, so hydrogen has 1 proton, and its atomic number is 1. Helium has 2 protons. Its atomic number is 2. All right, but helium, why is its mass number 4? It only has 2 protons. Why does it have mass number 4? What else do we add to protons? Neutrons, exactly. So can you do the math? How many neutrons must we have in that one? 2. We got 2 and 2. 2 neutrons and 2 protons, exactly. Okay. All right. Carbon, we all love carbon. We are carbon-based life forms, just like evolution would say. It's a movie, not a. So atomic number of the element carbon is 6. It must have 6 protons in it. Okay, this particular form of carbon has a mass number of 12. So it has, the total of protons plus neutrons is 12. So how many neutrons we got? 6. It doesn't always work out that way, yeah, but we definitely got 6.
It does not always work out.
It does not always work out that way. No. Okay. So I think this is my last chemistry slide. Sad, so sad. Okay, so we have hydrogen, helium, carbon. We talked about a minute ago. And that number 1, 4, and 12 respectively is the mass number. And it's the number of protons and neutrons that is in the nucleus. So the thing about it is you already see, there is one version of helium with a mass number of 4 and another version of helium with a mass number of 3. The deal is both of those have, since it's helium, it has to have two protons in its center. I will do it this way. I will ask it in the form of a question. Question mark. How many neutrons does that one have? 2. Perfect. Same question. How many neutrons does that one have?
1.
It does have 1. Why does it have 1? Yep, because its mass number bumped down 1, and you can't screw with the protons, excuse me, but I get excited about this. You can't mess with the protons, but you can mess with the neutrons. So basically, if you compare those two, the difference is 1 neutron bailed. Not easily. Very good. Okay. So isotopes have the same number of protons with a different number of neutrons. So that was helium. Here are isotopes of carbon. Have you ever heard of carbon-14 dating? Yeah. The thing about carbon-14, and it's right here, carbon-14 is one form of carbon, one isotope of carbon. This is what we call this is the most regular. I usually use the word abundant. So most carbon is that one. And some carbon has a mass number of 13. It's getting heavier. What do you think? Did it pick up a neutron or lose a neutron in its nucleus from 12 to 13? Picked up 1. So instead of 6, it's got 7. So here, if you compare carbon-12 to carbon-14, it picked up 2. So instead of 6, it's got 8 neutrons. That's kind of how all that works.
So the protons can't change.
Right, the protons
Just
cannot
the
change,
neutrons.
just the neutrons, yep. Yep. So here's the thing about carbon-14. Carbon-14 actually is kind of rare. I'll say rare, okay, and that's kind of an overstatement. It is unstable. Okay, but you're going to laugh when I say how unstable it is, because I read this the other day. I think it's like, it decays, half of it breaks down in about, I think it's 4,000 years. I just think that's funny. So if you had 10 atoms of carbon-14, you give it, 4,000 years, and you'll have 5 atoms of carbon-14. The other 10 will have just broken down into something else. It's called half-life. But it's unstable. I just think that's so funny. So the way we date things is, I know, I'm easily amused. So the way we date things is that, that's supposed to be the sun. Very good. And so when something is alive, like people, or this is supposed to be my flower, okay? That's terrible. What we do is, when we're alive, we are incorporating carbon-14, fresh carbon-14 into our bodies. It's like a sun thing, and it involves nitrogen and radiation from the sun. So just kind of think of it this way. Basically, our cells we got a lot of carbon in us, right? So as we're breathing and walking around here, we are adding carbon-14 to us. Okay, so I don't know how to, then this is going to be morbid, but so when we die, that's supposed to be a dead person. We stop with adding the carbon-14, and then the decay, the half-life, the 4,000 years sort of thing kind of clicks away. So basically what we do is, if it was a living organism, we can go back and we can see how much carbon-14 is left. Okay, and then we can use a little bit of math and backtrack to how long ago that thing was alive. That's carbon-14.
So is that how they know like how long a person's been dead?
What's that?
Is that how they know how long a person's been dead? Kind of.
Yeah, yeah, how long a person's been dead, yeah, exactly. And so then, like dinosaurs, they know how long they've been dead, sort of thing, yeah. And plants and ferns and,
Why would they say it's so rare if everybody has it?
well, I use rare kind of, and it's less abundant, it's less predominant. So just in general, if you're gonna go scoop up carbon-14, kind of take a representative sample, oh, sorry, not carbon-14. If you're gonna take a representative sample of all carbon atoms, the 14 would be really low.
Oh,
Yeah, yeah. But not really rare. Then the last term before we move on, one that you're probably already familiar with, is we kind of upscale from atoms to molecules. If atoms are bonded together, they can pair up and make molecules. Okay. And I just am amazed that part of what we know about outer space actually has to do with seeing trace amounts, for instance, of carbon monoxide, the molecule CO, out there in outer space. Yeah, you're like, wow, I know. It's like, really? And I'm going to say it a few times, but the whole thing about carbon monoxide, you're like, really? How can you use a telescope to detect that? And it gets down to the cousins, quite frankly. Okay, the cousins, like the light, okay, versus radio versus gamma. Okay, you select which wavelength you want to look at, or use, excuse me, depending upon what you want to look for. Pretty cool stuff. Okay. So all matter is made up of atoms, right? We just talked about it. So you kind of have a general idea of the structure of an atom. And it's funny because I'll go ahead and correct it. When it says light and matter interaction in various ways, instead of light, I'm going to say EM radiation. I think that's better. It's the cousin thing, okay? So those energies, you know, we're going to talk more about. Astronomy relies on those different energies. And those energies interact with matter different ways, depending upon the energy in the matter. So you're probably familiar with these terms, okay? Energy or light can be absorbed. That energy can just go through that object. That object can send it either reflected or scattered. There's very similar. Reflected is like a mirror, so you know how it's going to, what angle it's going to go back up. Scattered is just like, I don't know, but it's going to be scattered. Okay. So, kind of get you thinking. Here we have, and the word is, because I think we ran into this word last week, the word is photons, little packets of energy, little packets of light, little packets of any of those cousins, photons. So here we have someone in a projection booth sending photons to the white screen, probably like this, right? Okay, and those photons are scattering in all directions. I think it's, I was kind of looking at this at my desk and thinking about this. I think it's kind of neat. If you look, for instance, at this one little, look at the yoga's, looks like a Yoda guy. Okay, look at his mouth, for instance. And light is going in all directions, being scattered in all directions. So this person can see his mouth, this person can see his mouth. I know it's a small thing, but that light goes here and goes. Okay, so we can all are privy to that nose. So the theater projecting on a white surface is just scattering everything back. Okay, when we look in the mirror, say hi everybody. Okay, it's an angle thing. I mean, it's limited. The bouncing off is limited, and you can anticipate, just like they know how to look for that iridium flare today. We know the angle. It's different than scattering, but the similar thing is it just basically pings off, right? Yeah. Okay. So remember the mnemonic device, Roy G. Biv. Okay, and we talked about this last week, where red is what, the longest wavelength? longest lambda, and violet is the shortest. Okay. But I think this is kind of neat, and some of you guys probably already know this, but if we see an object as a particular color, let me go back. If we see an object as a particular color, here's how this works, and I have a slide to kind of show you. How does this work? Well, first off, when we turn on the light bulbs, okay, basically these lights are sending all colors, okay? Basically, there's gas in there, and electricity is exciting the electrons around those gas atoms, okay, and they're falling back down and they're emitting light, okay? They're doing Roy G. Biv, basically. That's my point. And so when we see this as blue, okay, basically blue is being scattered off and everything else is being absorbed. So you'll hear me say, Roy G. Iv is absorbed, blue is scattered off. I just think that's cool.
Well, when they was changing, people are going to these type of bulbs because it doesn't, but it's not as soft, and is that because there's not as much red in it?
Could be, when you start messing with the gas and kind of the technology of electricity, exciting the gas, you get a different, what we call spectrum. You kind of get a different, and all light bulbs have, like, if you go to Lowe's, they show you the different light bulbs and kind of the different flavor. Is that kind of what you're talking about?
Yeah, where it's, you want that softer. I don't like this type of light but I thought it was something to do with the red, being less red or something.
Yeah, yeah, you can mess with it and kind of get it, tune it to a particular way. So all this is doing is kind of showing you the green tree, okay? So snow was going to be here before we know it?
No.
Oh.
I don't like the cold.
Well, I don't. Maybe we'll take the snow without the cold. How's that? So have you ever gotten a sunburn from the snow? Shoveling it or playing in it? Yeah. So the reason is because can you see the Roy G. Biv from the sun, okay, hitting the white snow? The thing about white is basically it doesn't absorb anything. That's why we wear white t-shirts in the summertime. Okay, so everything comes back off. The Roy G. Biv comes back off and it burns our faces. Okay?
And it burns our eyes.
It does.
When it's a fresh snow, my eyes used to, if I drive on a highway, I can't have to pull off the road, they burn so bad.
It's not good. Do you wear sunglasses and still have issues? Yeah, some people's eyes are more sensitive.
Not so much now, but when I was younger.
I read that blue eyes are more, the most sensitive
Really?
eyes, and darker
I
eyes
do.
because of the light.
Are more, less sensitive? Yeah. Luck of the draw. So here's the deal too, like the green tree, okay, see it is absorbing everything except green, okay? So the green tree is gonna, actually some of that light is gonna warm up that tree. Here's one thing about it, like if you were to have a dark patch here in the snow somewhere, you think that dark patch would be kind of warmer? That dark patch is warmer because it's absorbing more of the energy from the light instead of reflecting it all back. So kind of in here, what your author did is have light coming from the lamp and light coming in the window from the sun and shining on that red chair. And of course, red, there's all sorts of possibilities here. Okay? I think you guys get the idea. Okay. Now, if I were to go back over here, and it's funny because you guys were like, oh, she has to be the sun, she has to be the moon, she has to be the earth, and now I get to be an atom. Okay, if I were to go like this, what would you say I am? Or what's my hands? They're electrons.
They're crazy.
They're crazy. Electrons are moving around, nucleus a little bit. Electrons moving around, okay. And actually, did you hear me a minute ago, when it comes to like giving us light in a light bulb, okay, you have gas in there, and it's the electrons around the gas atoms that actually are doing some movement when you pass electricity through them to give us the light. And that's movement, actually, we're going to talk about right now. Okay, so kind of what makes the light bulb light up for us is what we need to talk about with regard to something called spectra, spectral lines. So these lines I want to talk about are not entirely dissimilar from the gas in a light bulb. So electrons, I know I already kind of said they're crazy, got the energy going, okay? But the thing is, sometimes they're going this fast, and sometimes you zap them with electricity. And what I usually do is, if the center of me is the nucleus, electrons, I usually say electrons are excited, and I usually I guess kind of like that. Electrons are excited. They took a little bit of energy, and these are even going more. These are going less. These are going more. Okay, so electrons can actually be promoted. Okay, around. They're still part of the atom. They know and love. Okay, but they go to what we call an excited state. Okay, and that can happen from electricity, like in a light bulb. That can happen from heat. Okay, but excite that electron up. So here's one way to look at this. All right, here's the deal. If I'm a hydrogen atom, okay, I'm going to have something. This is going to be different. This is my electron. I'm exciting my electron. If I'm a hydrogen atom, that's going to be different than if I'm a helium atom. That's sort of how I respond, how I jump, how my electrons jump is going to be different if I'm hydrogen, if I'm helium, if I'm carbon. Okay, so it's a way to actually, if you know what you're looking at, and people do, okay, if you kind of look at those transitions, we call them, okay, electrons getting excited, moving up, electrons chilling out, moving down. If you know what you're looking at, you can identify hydrogen from helium, from carbon, from lithium, from iron, and you don't even have to go out there and take a sample. You can just look at the energies coming from it. And that's exactly what I'm going to kind of show you. It's a fingerprint. Do you guys remember the opener for chapter 5, and it showed like a rainbow, okay? And you saw kind of those lines, okay? Those were the fingerprint lines that we could actually understand what sort of gas we had, okay? Elements of what sort of gas. Okay, so I'm going to talk about Kirchhoff's 3 laws, okay? And sometimes my test questions will go like this. Basically, as I talk about this, what I want you to know is it's about the electrons giving us these 3 laws. But Kirchhoff's first law actually is the whole rainbow thing, okay? His first law has no lines, okay? And then kind of as I have them listed, and I'm going to show you some examples, his second law is emission line spectra. His third law is absorption line spectra. Like, what's all these dudes coming up with all these laws, right? So starting with the first law, it's basically just rainbow. Happy face rainbow. Okay? Then we get into, when you see some lines, whether it's emission lines or absorption lines, then we get into kind of the fingerprint. I'll go ahead and tell you that opening slide for chapter 5, that was actually dark line or absorption lines. So emission lines, I'll go ahead and sometimes I forget to tell students, but you'll hear me call these bright line spectra. Bright line spectra. And actually it's in its description right here. And you see the whole electron thing? It's all about electrons. Not for protons aren't important. Neutrons, don't tell them, but I think they're the least important. Subatomic particle. Okay. So basically we get emission lines if after it's excited when the electron falls back down. And kind of, I have a good picture, I think, kind of showing you electron falling back down, and it emits a certain amount of energy just based upon that little step. It's a certain step. The next one, the absorption line spectra. I'll go ahead and put all these up. The absorption line spectra, oftentimes I call not bright line, I call dark line spectra. It's not just me, it's what they do. Absorption line spectra are dark line spectra. While I'm here, I'm going to go ahead and take emission line and absorption lines. Are you familiar with, I don't know if I'm familiar with it, but like if you get a negative, like, you know, the old time you developed your pictures, okay, and the negative was like the opposite. And so these are negatives of one another. So they're the same fingerprint, but they're negatives of each other, okay? You'll see what I mean. I have some example negatives of each other.
So it's when they go up.
The last one?
Absorption, yeah.
Yeah, the absorptions went on the way up. Yep, absorption's on the way up. They take a little bit, they suck a little bit of energy on the way up. That's absorption, okay? If they're already up there and they fall back down, that's emission. Okay. So I'm thinking this is like information from Mars. I'm thinking if you read the context in your textbook. So basically, we can point our telescope and get a signal from a planet like this. Okay. Now we're going to be looking at several of these. Let's kind of orient ourselves. What we got going on. Okay, down here you see wavelength, and hopefully you see the Roy G. Biv, right? So this is just one cousin, isn't it? This is just visible light. Cool. So you see over on the y-axis we have intensity. Intensity at that particular color. Okay. And then this kind of purplish line is showing you the intensity. The higher that line is, okay, the more intensity is at that wavelength. That's how that goes. So can you see, to me, I'm just looking at it, and it kind of looks like green, for instance, is the most intense of all the colors. Does that make sense? Just kind of, just because it's the highest. Okay, so you already see it. Can you see where these little spikes, you're like, it's like, kind of looks like it has a trend that has these little spikes, okay? Can you see where those are emission lines? Does it sound like emission lines?
It seems kind of backwards. Like it looks like the emission lines are going up, and then it looks like the absorption lines are going down.
So the emission lines are going up. The emission lines are kind of going up along with regard to intensity. They're like little burps of energy.
But I thought the emission line was when it came down.
Oh, I see your point. You're right. So the thing about, we were talking about two different things. The thing about emission is energy emitted. And when can energy be emitted is when an electron is falling down.
Oh, okay.
Yep. So it's kind of like, it happens simultaneously, like electron falls down and light emitted. Yep. Very good. So then over here, can you see where those are kind of like little, it looks like it should have a trend, okay? Then we see like little, it's robbed of energy. And then if you look below there, those are the particular wavelengths that are being of red. I know it looks all like red, but these are varying wavelengths getting longer and longer and longer. These are, if you had a crayon box, these would be subtly different colors in front. Okay? So these are just, sucking them up. Why? Because it's a particular element, or maybe compound, that's going to suck those because of how the electrons are arranged. Are going to suck them right there. And what does it do? It lowers the intensity, just momentarily. And so that would be Kirchhoff's third law, absorption, dark line. And then, of course, your slide says this is continuous. Why? No lines. Okay. And then kind of going over here, what are these? Are they absorption or emission?
Absorption.
They are absorption. Yep. Yep. So that's kind of how that works. These are cool. Let's see. So I don't know if you can see, it says, toaster oven, neon lamp, a star called Spica. And this is, the last one is, what would it look like, what would energy look like if it was coming from a green leaf? Oh, you're fine. So the first one's the sun, okay? Looks like a continuous spectrum, Kirchhoff's first law. Toaster oven filament. Ooh. Okay, I buy that. Toaster oven is basically, remember I told you the other day, infrared is on the other side of red, right? And infrared is actually heat, so, okay, let's see, neon lamp. Ooh. Our eyes just kind of blend all that together. It's a neon lamp. Isn't that cool? Blue star. Whew. Kind of a continuous like. Oh, it looks continuous, but look where the peak intensity is. Remember the y-axis is intensity. Okay, it looks like it's got more energy over here at the shorter wavelengths and less over here. Okay, and green leaf. So leaves look green, and it's like a molecule chlorophyll pigment sort of thing, okay? But if we were to kind of analyze the light coming from a green leaf, it looks green, that's the most intense color, but it's got a little bit of the other colors, okay? So, one more. Let's do this one. I think I like this one. Oop. Maybe. No, I'm not going to. Well, okay. So, Kirchhoff's first law, you get a continuous spectrum. Okay. And notice, though, that this is the low temperature. What do you think is going to happen if I jack up the temperature? You think it's going to go more toward infrared or more toward ultraviolet? How many people think infrared? How many people think ultraviolet? It is ultraviolet. And after break, we'll talk about something called, I can't remember which law it is. But even though, I know why you would say infrared, because I said infrared is heat.
Yeah.
But more energy, the more you go towards the gamma rays, the more energy it is. So it's kind of peaking there. Let's see. So that was continuous spectrum. Okay. So to get an emission spectrum like that, basically I said electrons were promoted and they fall back down. Well, what you need to do is have some sort of gas that's like in your light bulb that's been electrified, or electrons have been excited around those atoms so that they can fall down. So what do you think if I jack up the temperature? Now those are fingerprints now. So do you buy this? That it's a fingerprint, in this case a set of 4 lines, that they're going to stay there. They're just going to get more and more intense. It's a fingerprint for what that gas is. So the absorption, actually, the way it's configured this way, where this cloud is absorbing some energy from that light, okay, and we're seeing a little bit of suck up. The last one I said 4 lines. Do you see 4 spectral lines here? Yeah, and they're dark lines, but they're like the negative. Exactly. So if I jack up the temperature, I guess it's going to stay 4 lines. Okay, but the absorption is going to increase. Okay. I think this is a good place to take a break, and we'll come back in about 10 minutes or so. What did I say we were gonna do? Gonna, the chem lab.
Something at the Are we gonna have to do the slide, the next slides, or we should put them on?
What? Oh,
Put chapter 6 slide.
I don't think we're gonna get to chapter 6. Let me see how far we are. This will go pretty fast, but I think, yeah, don't worry about turning off chapter 6. And sorry, Becky, you turned off chapter 6. Sorry. Hey, you guys, we're not gonna get to 6, 7, just 5. Okay. I think we'll come back. I'll write a little note to meet us in the chem lab, I think.
This and then just I'm trying to mark each one, so maybe it'd be easier for you to see. When they changed my mind, which things, it's all.